what we're going to do now is our first real Calc 3 limit. But I'm going to start the same way I did before, because if I can plug in, I'm going to try it. If I plug in on a 0, 0 on top for x and y, I get 0. If I put a 0 for x and 0 for y on the bottom, I get 0. So I get 0, 0. Calc 1 technique said, do some algebra so you can cancel, but there's nothing you can really cancel here that actually helps at all. And the second thing we're going to try every time we do a multivariable calculus limit is to see if we can't show the limit doesn't exist. Now, just a reminder, yes, what it means in Calc 1 for limit doesn't exist, it means the limit from the right is different than the limit from the left. And there was actually kind of convenient because you could only come from the right and you can only come from the left. But here, what we need to imagine ourselves is standing on that surface, and the origin is over there someplace. And what we want to do is start from any point, taking any path, and walk ourselves on the surface until we're standing over the point 0, 0, or almost standing over the point 0, 0, and ask ourselves, how high would we be when we got there? Now, there's an infinite number of paths we could take from the point x, y to the point 0, 0, and so in general, we have to pick some paths. We generally like to start with just linear paths, so I'm going to pick a nice, easy linear path. How about just something like path? I need the path. How about y equals x? Now, what does that say? If the origin is here, what I'm going to ask myself to do is I'm now just going to, instead of squiggling, I'm going to walk on the surface, yes, over the line y equals x until I get there. Now, why does this help? Well, I now can put an x anywhere I see a y. So, for example, the top thing becomes x squared. The bottom becomes x squared plus x squared, well, that's 2x squared. And the limit, and I'll only write it this way once, and then we'll write it the way we're supposed to, is as x goes to 0, 0. Well, that's a really stupid way to write it, because if x is going to 0, x is going to 0, and we'll never write it that way again. We'll just write it and say, look, we have just a function now for our first real multivariable calculus limit. But I want to start it the same way I did before. I want to put a 0 in for x and a 0 in for y and see if I can just plug in. Because if I can plug in, I don't need anything fancier. But if I put a 0 in for x and a 0 for y on top, I get a 0. When I put a 0 in for x and a 0 in for y on the bottom, I get a 0. We know from Calc 1, we call those indeterminate, so that's not going to work. There's no way to use L'Hopital's rule. In this particular case, there's no nice algebra I can see that's going to work. And so the second thing we're going to try every time we do a multivariable calculus limit, after the Calc 1 limits techniques don't work, is we're going to try to show the limit doesn't exist. Now, remember from Calc 1 how we show a limit doesn't exist, right? If we have a function that does this, and that function does this, we say, ooh, the left-hand limit is different than the right-hand limit, so the limit doesn't exist. Another way of phrasing that is as I walk on the graph from the right, I get a different answer than when I walk on the graph from the left. It was nice in Calc 1 because there were only two directions I could go, from the right and from the left, to get to the point. In Calc 3, it's much more complicated and actually much more interesting because of that. This z equals xy over x squared plus y squared is a surface. We could probably make a Plato model out of it if we tried really, really hard. But the idea here, right, is that the origin's over here, for example, say, and we're walking on the surface. And the idea is we want to know as we walk on the surface, how high are we going to get when we actually get almost to the point while standing on the surface? Well, if I'm going to try to show the limit doesn't exist, I want to pick two different paths and get two different answers. But this is more complicated because there is no just from the left and just from the right. There's any path at all that I can walk on while staying on the surface, and I want to see what height I'm going to end up at. So generally what we do is we try to pick a path. Linear is usually a good one to start with. I'm going to pick y equals x because it's just the easiest one. Now what does that mean? That says I'm not going to go squiggling around here as I'm walking on the surface. I'm going to pick just the line y equals x that's lying underneath me. Yes, and I'm just going to walk on the surface, whatever it does. and I want to know how high I'm going to be when I actually get there. Algebraically, this does a lot of simplifying for me, because if y equals x, the xy on top just becomes x squared. If y equals x, the bottom just becomes x squared plus x squared. Well, that's just 2x squared. We're still trying to take a limit. Now, the thing about it is, this is now just a function of one variable. And so I'm not going to write down, for example, that the limit of x goes to 0, 0. That's now redundant. I get to just write that x gets close to 0 instead of x gets close to 0, 0. Now, this is now a Calc 1 limit. What can I do? I still can't plug in, but I now can cancel. And I get a 1 on top. And what we get is 1/2. Now, what does that mean? That means as we walk on this big squiggly surface, but staying over the line y equals x the whole time, we will arrive at the height 1/2 when we get there. Now, let's just take a slightly different path. We can take many different paths for what it's worth, and we'll explore that in the next example. But what happens if I just pick something like y equals 2x? Now, what does that mean? Again, it's the same squiggly surface that we were on before, but instead of walking over the line y equals x, we're now walking over the line y equals 2x. And we're going to stay on the surface, and the idea is about how high will we be when we arrive at the point? Well, writing down even anything simplifies a lot. Instead of y, I can now write 2x. The top is now x times 2x. That's just 2x squared. The bottom is now 4x squared plus x squared. That's now 5x squared. We're still taking the limit. Instead of writing down xy goes to x, I'm sorry, x2x gets close to 0, 0, we're just going to write x gets close to 0. And we're back in our Calc 1 case. I can't plug in, but I can cancel. And after I cancel, we can now plug in, and we get 2/5. Aha! And what does that mean? Remember, if I walked over the line y equals x, I end up at height 1/2. If I walked over the line y equals 2x on that surface, I end up at height 2/5. For us, that is actually a way of showing that the limit doesn't exist. It should certainly be true if the limit exists, that no matter what path I take to get to the point, I should always arrive up at the same height. And so we need a little conclusion. We're going to say the limit does not exist. And I think that's enough for now. Okay,